So Diana very colourfully and powerfully laid out the drivers. What about the impacts now? Let's introduce Steffen, who scarcely needs an introduction, really, having run the International Geosphere-Biosphere Programme for many years. He's now the Executive Director of the Australian National University's Climate Change Institute. Steffen, where are you? There you go, Will.
Back here. Thanks very much. And again, thanks to the organizer for inviting me. It's a great honor to be here. Well, I'm going to follow on directly from Diana and talk about, well, what is the impact of all this human activity we've seen, particularly since 1950? So I'll use the same style that Diana used, these 12 panels of graphs. And again, look at the overall shape of those graphs. These are the biophysical consequences of the increasing human activity, particularly since 1950. The top three are the famous greenhouse gases, CO2 in the upper left, and we have ozone depletion, a couple indicators for climate. The bottom six are interesting because they don't relate to climate. They relate to direct human impact on element cycles and on the structure of the biosphere, both marine and terrestrial. Now you see, again, 1950 is a pretty significant year, and we definitely see human impact in almost every aspect of the Earth system we could look at. And in fact, I'll talk a little bit later about this concept of the Anthropocene, and it's really based on this set of panels. But then these stop at 2000. The question is, have any of these trends turned around in the last 10 years? Well, it's hard to see trends change in only 10 years, but let me show you a few of them. CO2 concentration, despite the decrease in energy intensity that Diana referred to, we see no significant change in the CO2 trend. In fact, it's slightly increased in rate over the past decade. Northern Hemisphere surface temperature, again, that's gone up from 2000 to 2010, pretty much in keeping with the trend that was established in the 20th century. Here's one where we do see a change, and humans have, in fact, reacted to the stratospheric ozone problem through the Montreal Protocol, and we see that even a little bit before 2000, stratospheric ozone depletion has leveled off and is continued level. It'll take some decades for that to start to recover. That's the lag in the system itself. But it looks like we might be getting this under control. Here's loss of tropical forests and woodlands. Again, unfortunately, that is continuing over the last decade. It hasn't leveled off yet. And if we look at coastal structure, we see a really rapid increase in prawn farm production, and we use that as an indicator for conversion of natural coastal ecosystems into production systems. So a lot of these trends really haven't turned around yet. But I think it's important to move from individual indicators and take a more systems approach to what this pressure on the planet really means. We can do that with a couple of the big element cycles. We've already talked a lot about the carbon cycle. This is what the whole system looks like. Above that horizontal line are emissions. And you see those brown emissions from deforestation, which are important. But again, since 1950, they've been absolutely swamped by fossil fuel emissions. That's the #1 problem in terms of the carbon cycle. Below the line are where does that carbon end up? It's interesting, only half ends up in the atmosphere. The other half is absorbed about equally by land and ocean. If we look at the nitrogen cycle, it's been changed even more than the carbon cycle. All you need to do in this complicated figure is look at that big fat arrow of N2 unreactive nitrogen coming down through natural processes in the top panel, but you see an additional huge arrow coming down from N2. That's human fixation through the Haber-Bosch process primarily of unreactive nitrogen, used primarily as fertilizer, but then you see the width of all the other arrows changes as this goes through the environment. So very significant changes to how the nitrogen cycle operates. Let's now focus a little bit on climate. It's obviously a very important topic, but there's a lot out there, so I only want to summarize what the major trends are. This is the one most people look at, which is global average temperature, the Earth's surface, and you see again the trend out to 2011. A lot of interannual variability, but the trend is upward. When we smooth that with an 11-year average, we can see the trend has continued. Again, the trend that was set in the second half of the 20th century has continued from 2000 to 2011. But there are other aspects we can look at. That's the loss of the Arctic sea ice. Again, it varies from year to year, but there's no doubt there's a downward trend, and we're heading for an ice-free Arctic Ocean sometime later this century. Sea level, very important for human impacts. Again, that has increased throughout the last century and continues to do so. In fact, if you look at the last 20 years, the rate has increased somewhat, over the overall rate over that 120 or 130-year period. Again, we see no decline in the rate since the year 2000. Now, this is the graph that to me is the most important of the climate graphs, but you rarely see it in the news. This is ocean heat content. This is important because 80 to 90% of the extra heat at the Earth's surface due to the extra greenhouse gases actually ends up in the ocean, not in the atmosphere or in the ice. And again, we see since the middle of the 20th century a clearly upward trend, and that has not slowed down at all from 2000 to 2010. So the basic summary of this part of my talk is these trends that were established during the second half of the 20th century in terms of consequences of this human activity on the Earth system, by and large, are continuing unabated so far into the 21st century. So we have yet to make any significant inroads in turning around, I think, some of these most important trends. Climate extremes, that really affects a lot of people. For the first time, I think we're starting to piece together the role of climate change itself as opposed to climate variability in these. The IPCC very recently released a report on this. And in two areas, temperature extremes and increase in coastal flooding, there's a likely contribution of climate change now that we can see in observed events. Intensification of extreme rainfall, just medium confidence. There's still a lot of discussion in the community about whether we see a climate change signal and how important that is. I want to now talk about the Earth as a complex system because we as scientists like to pull pieces apart. That's how we're trained in our disciplines. But it's important to realize that the Earth as itself operates as a single system. We see this beautifully in an ice core data from Antarctica, and I've just indicated on that middle red line, which is a temperature line, that this encompasses the entire time that humans have been on the planet, fully modern humans. Most of that time we've been hunter-gatherers. It's only in this last little period that I've shaded here called the Holocene, last 12,000 years, where we first began agriculture, then villages and cities, and now contemporary civilization and the great civilizations that occurred before us. This is sort of a special time in Earth history that we've taken advantage. So the question is, are we actually pushing the Earth itself out of this rather stable state, at least in terms of temperature? And it's this sort of question now that we're starting to address in science. Here's one way we attempt to do this. This is a nearly 2,000-year temperature record from the Northern Hemisphere, where we've used proxy data to estimate what the temperature might have been before we had thermometers. And you see the various estimates. You can see warm periods in the middle of that, the medieval warm period. Little ice age appears later on. But that red line I've circled is the contemporary greenhouse gas-driven temperature rise over the last century or so. And you see it's different. It's now moving the Earth system just beyond the limits, at least of the last 2,000 years, perhaps back to the mid-Holocene. And it's occurring at a rapid rate. It's this sort of evidence that has triggered the term that you've heard used a couple of times, the term the Anthropocene. It was first used, I think, in the year 2000, quite fittingly, by Paul Crutzen, the Nobel laureate for his work on the ozone hole chemistry. And it's now being debated in the geological community. Are we really moving into a new epoch in Earth history? And it's because of all these human drivers that Diana just told you about and the impacts that you see on the bottom of that slide, whether it's nitrogen cycle, carbon cycle, climate, biodiversity, what have you, we are moving the Earth out of that Holocene domain of stability. And that's why this term Anthropocene is taken off, and even in the last year has become popular out in civil society. So I want to now focus on the second half of my talk about what the Anthropocene really means. And I want to use this theme of looking at the Earth as a complex system and looking at what complex systems, how they behave, how they operate, and what are some of the risks associated with putting a lot of pressure on a complex system. One of the ways we can do this is look at these so-called tipping elements in the Earth system. And I think Lita referred to those earlier in her talk. This is one map showing where some of these are. You can read what they are. I'm not going to go through all of them. All I want to do is highlight 3 of them and show you the first bits of scientific research on them that just give a hint of what the risks might be. But there's by no means much certainty around these, but it shows where we need to do more work. Let's start with the big polar ice sheets. They're very important, particularly for sea level rise, but also for the stability of how the planet operates. If you like, they're great refrigerators that slow down the warming of the planet. If we look at Antarctica, we see that most of it, East Antarctica, color-coded here, doesn't show much change in terms of the mass of ice. It appears to be very stable. But that colored area on the left is West Antarctica, and that appears to be losing mass now over the last decade or so. There's actually more concern about Greenland. In fact, there's more data about Greenland. We've done more work on that. And when you look at the trend color-coded, where red and orange are where ice is being lost, blue is where ice is actually being gained by increased snowfall. When you look at the overall balance, it's dropping rather rapidly from the 1990s to the present. And we're now losing mass at the rate of about 200 cubic kilometers a year from Greenland. Now, the interesting thing here is it takes a long time for these ice sheets to disappear, but we could actually reach a tipping element within the next few decades of this century, where once we cross it, they will be committed to being lost no matter what we do. We can't change that direction. That's typical of a complex system. When you cross a threshold and the system starts moving to a new state, you can't stop it. Let's now look at a biological one. We'll look at the Amazon forest, where there's a lot of concern about that big carbon sink. Climate models have been used to project what might happen to the climate, and that upper panel shows where climate models are projecting a loss or a drop of rainfall through the coming century. The bottom panels indicate very severe losses of rainfall. And you can see that most models agree that we should be seeing a drier Amazon as the planet warms. Now, the interesting thing is it's the indirect effects, perhaps through fire, combined with land use change, which will actually cause the impacts. Now, we've seen two large droughts in 2005, and one in 2005, one in 2010. And that's the Amazon basin cut out of the map of South America there on the lower right. And it's color-coded where the browny or the yellowy colors are where there was a loss of carbon, where it was very dry and so on. And we estimated how much carbon was lost. And it turned out to be 1.6 billion tons and 2.2 billion tons in 2010. When you actually look at what that means, it actually undoes about 10 years' worth of carbon sink activity. So this could be one of the first signs that we may be losing the strength of the terrestrial biosphere to offset a quarter of our greenhouse gas emissions, CO2 emissions. Finally, I want to look in the far north, up in Siberia or across the far north, about the permafrost issue. Now, the issue there is that if you look at those purpley areas, that's permafrost that stores an enormous amount of carbon frozen in the soil away from the atmosphere. And it's been stuck there since the last ice age at least. It looks like this. These are lowlands with a lot of swamps, a lot of peatlands and so on. If you actually look at the soil, it's frozen down through the soil profile, sometimes to as deep as 200 meters. The concern now is what's happening to that area. And the concern is that there's a lot of carbon there. There's about 1,600 billion tons or petagrams of carbon. The thing to remember in your mind is that's about twice the total amount of carbon in the atmosphere today. So there's a lot of carbon stored there. The issue is this. If we look at a map showing the geography of climate change, of temperature change, and look at the last 3 decades compared to this 1970 to 80 graph, you'll see where the warming is occurring preferentially. There's one decade up to the 80s, there's the 90s, and there's the last decade. So you see it's preferentially warming in the northern high latitudes. We just put that on a chart, and you can see latitude 60 to 90 on the right-hand side of that chart is showing by far the most severe temperature change of any part of the planet. And of course, that's where the permafrost is. So what we've done is the Global Carbon Project has organized a permafrost carbon network, and they've asked 40 experts who really understand this system, what is the real vulnerability of this? And you can see the numbers on the top. If we take a high warming scenario, this is a worst case scenario for the rest of this century, you see that large amounts of carbon, by 2040, perhaps 30 to 40 billion tons of carbon could be activated, up in the hundreds of billions of tons by the end of the century. Now, just by comparison, fossil fuel emissions that I showed you are about 10 gigatons per year. So these are significant amounts of carbon. It's what we call a positive or reinforcing feedback. Another one, which is even more speculative, but a really interesting one, is that as these soils warm and as the microbes go to work and start activating the carbon through chemical reactions, those reactions are exothermic. They actually generate heat. So you got a self-reinforcing process here. As more and more of the microbial respiration occurs, you heat up the soil, and you may lead to a tipping point where heat is produced faster than it can be dissipated, and that's the so-called compost bomb. Again, these sorts of things are typical of a complex system where you get reinforcing feedbacks or dampening feedbacks, you get thresholds, you get abrupt change, and once these changes occur, they can be largely irreversible. They can't be stopped. So let me conclude then with stepping back and looking at this whole thing again with Earth as a complex system. It's basically existed in two states since humans have been here in the so-called late Quaternary. The ice ages, which tend to be long, erratic, and very cold by our standards, and then these short interglacial warm states, and that's the one we're in now. That's much more amenable for human life and human society. But we can also look at it in another way. We can look at what's called limit cycles in complex systems theory. And what do I mean by this? Is if you look at CO2, which is that one, or methane, which is that curve, or temperature, which is that curve, they are bounded at the upper and lower limits. They cycle between tightly set upper limits. Now what's happening is that that's where the CO2 limit is now. We've broken that enormously. We've doubled it. There's the methane limit. It's up there. So we have, without a doubt, broken out of those limit cycles for the greenhouse gases. We don't know for sure what the long-term consequences are, and we're starting to move out of the temperature. So another thing that we want to look at is the periodicity. About every 100,000 years, the Earth cycles between an ice age and a warm period. That's what's called phase locking in complex systems terms. It's a way to keep the system locked in that oscillation between ice ages and warm periods. So let's finally look at that graph I showed you of the last nearly 2,000 years of temperature with that red curve on the upper right hand there showing where we are today. But I want to put the IPCC projections on the same time scale, and that's what they look like. So from 2000 to 2100, there's a huge uncertainty about where temperature might go. It ranges anywhere from about 1.5 degrees up to 5 degrees or so, depending on emissions and the sensitivity to those emissions. But the point is, this is a huge jolt to the Earth system in terms of the state that it's been in. And we can say, well, there we are now. We're committed to this much simply through inertia in the ocean-atmosphere system. And as Bob Watson said last night, we'll probably go at least to 2 and possibly more. But under a worst-case scenario, it's very likely, I think, that the Earth system will move to a new state of some sort with a very severe challenge to contemporary civilization. Some people have even talked about a possible collapse. So again, from complex systems terms, this is what it looks like. Could we return to a Holocene-like state, cap temperature to 2 to 3 degrees, and cap these other environmental changes that we've talked about, and let the Earth come back to its attractor, if you like, the Holocene, where we know humanity can thrive? Or are we going to cross a bifurcation point or a threshold, some point beyond which the system will just shift to a new, much hotter state of the Earth system? So we had some wonderful questions from our young people. I want to leave you with a final question, which is the Anthropocene in the year 2012. We really are at the cusp of some big changes. My question is, where on Earth are we going? Are we going to return to a Holocene-like conditions? Can we actually get our act together and turn the ship around? Or are we going to an uncertain future? Not necessarily a disaster, but an uncertain future on a much hotter planet. Thanks very much.
Well, don't go away, come along. Amazing slides there, weren't there? Thank you for those. Crystallization of a lot of research. Some people sent us messages saying they wanted to see more of the slides and less of your face. So that's what we did.
I would agree with that very much.
And we're going to put the slides online as well, so you can digest them at your leisure, if that's all right with you. Yep. So they're available to everyone.
Absolutely.
Lots of questions coming in. I'm just going to hit you with one, which is from Rosie Robinson from the Global Sustainability Institute. And she asks, which tipping points have we already passed?
Well, the Arctic sea ice we've probably already passed. I think we're committed to losing that. That's an interesting one because it's not irreversible. If we could somehow cool the planet back down, you would form ice again. I think that's the only major one that we've crossed so far. Okay, so there's all to play for then. It's in our hands, really. As I say back down in Australia, we call it the critical decade. This is the critical decade. If we don't start getting those curves turned around this decade, we will start crossing those tipping points. And can we, do you think, really? Yes, but we're running out of time. We're running out of time. We can't say another 5 years, let's go on and then revisit it. It has to start now. It should have started, as Bob Watson said, a decade or 2 decades ago. This really is the last call this decade. Well, thank you very much. Thank you. Well, Steffen.